Okay, so as usual, if you have any questions, either feel free to speak up or to type in the chat. I'm going to go ahead and screen share to show you guys some new things. Really quick share screen. Okay, discussions. Here we go. So you guys may have seen this, and if not, then make sure to go ahead and go to the Chem 2141 section in Canvas. Once you're there, go to discussions, and it'll be the only thing currently posted, the HOLA ChemX discussion and poster. So if we open this up, we can go ahead and see that this is the portion that was from the syllabus that we discussed very briefly, but I'm going to go ahead and go through this today. So this discussion section, you're going to want to go ahead and complete into the discussion area here. And I believe you either add the discussion here or you comment on this. I'll have to ask Dr. Rastogi. Let me go ahead and put that down as a comment. Okay, so basically, this is very simple, super easy. 3 questions that you're gonna have to answer here. Question 1 is, what's your favorite food? And have you ever cooked that on your own at home? Secondly, they're going to ask you to find one organic chemistry technique or organic chemistry reaction involved in cooking of your favorite food and describe how. So even if your favorite food is Hot Pocket, then you can say, you know, the chemical reactions of performing it in the microwave. He also mentioned that you could do it like saying, you know, using an oven, baking food, the stovetop, using a grill, you know, maybe going outside and burning charcoal and cooking steak. You can look up the science of that. This is a freebie, so, you know, just respond to it with some detail and you most likely will get the full credit for it. And then question 3, finally, watch the videos that are listed here. You'll have video 1, TLC, extraction 2 phase separation, column, oxidation, decoloration of red dye, and the esterification reaction with glycerol and citric acid. And a lot of these are performable at home, but the main thing that he wants you to do is to review these so that way that you can actually go forward and create your own PowerPoint poster slide. So let me stop sharing so I can open this up for you. So if you click here, it'll open it, but it's not going to show on my screen until I switch. So if you click on there, it will give you a poster template. And let me go ahead and open that up for you guys. It is a presentation template. Okay, so this is what it'll look like. So here, material and hazards, you know, basic information to state what you're going to be utilizing within your experiment. The procedure here is the, you know, stepping stones of how you would perform your experiment. The possible chemical reaction stoichiometry, you can go ahead and look on Google and look at some images there. You can maybe even draw it in Word and place it into here. The main thing that he wanted me to inform you guys about right here is this photo or table or graph. It would be very interesting that if you perform this experiment at home, that you go ahead and just take a photo with your camera or your cell phone and upload it. So that way that we have, you know, a real life image of something that you performed. It can either just be like the reaction itself or you next to it. Then the 4th portion, data analysis, you know, what did you see? What did you find from the experiment that you performed at home? Then your conclusions right here. And then of course the references, acknowledgements, it will be, you know, standard format of if you were doing some sort of research paper, then you can use links to maybe a website or article that you found that will show you the stepping stones of this. Make sure at the top, your first name and last name, your email right here, then keep this the same. This is our chemistry, our section 303. And the group number, don't worry about that part. You can remove that since we don't have groups. And then IA name, my name is Scott Barrett. You can find it spelled here in this Zoom meeting if you want to write it down or within the syllabus. And yeah, so let me double check that I said everything regarding it. It's pretty simple. You're going to have, you know, your own home experiment that you're going to perform and make sure that it's individualized. Let me switch my share back over to that section to what he said do not do. So you're going to want to make sure, let's see, not allowed. Science fair style and organic chemistry. So when he says that, he says, you know, like, don't do the very basic volcano experiment with just like vinegar and baking soda. And the poster cannot be a copy and paste, so no plagiarism. If you want to utilize it as a resource, just make sure to, you know, reformat it just the same way as you would be doing for a research paper. You're allowed to use the information. Just make sure that you utilize it in your own words, and then you give credit where it's due at that last section for the acknowledgments portion. And so again, if you have any further questions with regards to that, feel free to go ahead and type in the chat and I can clarify it. Let's see, we have a couple comments here. Template link is currently locked. Okay, yeah, so the food part, that is possible. I would say to go ahead and, you know, if it's kind of more complicated, that would be good, because you want to make sure that it's you know, big enough to perform a full experiment with, and not just, I put a cup of water in the microwave and boiled water, and now I have hot water. So yes, you will perform the experiment. It doesn't have to be, you know, drastic. You can just use Google and search up how to, you know, at-home experiments and such. And I see someone said that this would be the template is currently locked. So let me go ahead and write that down as a note to email Dr. Stogie. So template is locked. Okay, so you're saying when you are in discussions and you go to it, it's not opening. Okay, I'll make sure to contact him immediately after this.
Yeah, I'll
this
copy
one,
and paste the message it gives.
Okay, yeah, let me go ahead and tell. And if you always check the syllabus, let me go ahead and open that up real quick. It is not due immediately. This is just the opening. So on the syllabus, it shows that it was open today. Let me reopen the syllabus for you guys. And share screen. One moment. Where does this minimize? Share screen, syllabus, share. Okay, and then if we go down, let's see right here. Yeah, this is the grading section for it. Let's see what I can do. So all the way to our group C schedule. So today, well, it was technically supposed to be opening last week, but it's open now, and I'll tell him to make sure to open it. The discussion closes and the poster is closed on Saturday, May 1st, 2021 at midnight or 11:59. So make sure, double check right here. This is the only thing I can see from here that you guys will have separate from your normal weekly duties. So just make sure to slowly, you know, work on it. It's one of those things that's best to, you know, do it in college as well, is to just slowly work on a project and don't wait till last minute, because you're going to fumble it. You're going to be emailing me questions on, you know, April 30th and be like, hey, oh my gosh, Scott, I didn't do it. What do I do? What do I do? And I can, you know, help you guys out with some helpful, like maybe some links or something down the line. But if you're asking me, you know, the week before it's due, most likely, even if I give that to you, you're going to be staying up for a night or two to try and crunch that out. So try and do it earlier than later. It's a good practice within college in itself too. I know you guys are probably sophomores, maybe juniors in this class, but with regards to any sort of big projects, you will always want to do it over the course and not, you know, try and cram it all in at the last second, because you might just lose some unnecessary points because you just, you know, oh, I had to do it last minute last night and I forgot to put my name. It's like the worst thing to lose some points on. So, you know, spend your time. You guys have February, March, April. You have about 3 months to complete this. So that's ample time. If you ever have questions regarding it, feel free to email me. And yeah, so if you guys have any further questions, go ahead and go in the chat. Otherwise, I will go ahead and close this off and open up our current topic for today. So with regards to being 3 months, you know, you just have to fill out the poster template. It's not going to be a paper. It'll be just that poster format, and it would be as if you were going to be, you know, showing the poster at like some sort of small science fair. But yeah, just make sure that it looks, you know, nicely styled and an adequate amount of information on there. And I'll see if maybe he has a poster example, possibly. I'm gonna go ahead and write a note about that, and then we can discuss that next time, or I'll send you guys that in a link. Okay, so on to today's subject. Oh yeah, let me open up the module first. Okay. So this week we have TLC in column chromatography. Now, I love this stuff. I don't know how many of y'all here are chemists, but if you are, then you most likely will be utilizing this within lab performing research. And so firstly, make sure that you guys read through the lab manual, probably did for your quiz. We will be reviewing that here shortly. Secondly, make sure that you guys watch all these videos. They're about 20 to 40 minutes each, so we're not going to go through them. If you have any particular questions and maybe it's a little unclear as to certain things, please feel free to either type in the chat or speak up. I personally love this subject because it is so useful within chemistry, especially for separating compounds. It's really amazing how you can synthesize something and have 100 different things in your mixture and be able to just pull one thing out. And not only is it useful within research, this is useful within the industry too, with regards to creating things that we use on a day-to-day basis, and they can pull it out of a giant reaction mixture in this massive cauldron where they create these things. So this is extremely important within the science community. So make sure to go ahead and watch these videos, and if you have any clarifications that you need from the videos, always feel free to speak up or email me personally. Thirdly, the pre-lab notebook, we will go forward to review that, and the quiz, hopefully you guys completed that one already. Then let's see, yeah, Group C, we're here, we made it, that's great. And it looks like this is mislabeled for the date. But anyways, going forward, after the lab day, make sure to work on your post-lab notebook and submit the completed version. I will go ahead after this class to make sure to review y'all's notebooks and finish up on the quizzes as much as I can before I have to go to class today, so that you guys get your grades as soon as possible. So since this is a brief overview, I'm going to switch back. Let me go over into, let's see. Okay, so for this one, and I'm gonna make sure that I'm gonna go ahead and write down right now the people that I choose for the pre-lab notebook, so that way that I can just do it randomly every week. If I choose you again this week, my apologies, just because I didn't review who I did last week. So I'm just gonna go ahead and choose, let's see, how many total, 25 participants. So I'm going to choose 7 quick students to check your pre-lab notebook. If I type your name in the chat, then just go ahead and either screen share, which let me go ahead and open up the additional multiple participants can share. Okay, and I will type out 7 names really quick. One, 2, 3, 4, 5, 6, and 7. Okay, and I'm gonna go ahead and write these names down, and then that way I can randomize it next week. So, if you don't show this week, then, make sure that you have it for next week as well.
Is there a certain order, or can I just show you now?
You can just show it. I just need to see briefly, either the physical or your screen. Okay, great. Yeah, so just make sure you got all of your stuff up there, and yeah, exactly like this. Like you're gonna walk in the lab and be able to perform the experiment. Okay, great. So Jordan, you're good. Alex. Okay, awesome. Thank you, Alex. Okay, Nadia. Okay. Great. All right. Thank you, Nadia. And make sure, Nadia, whenever you write up your pre-lab, just as a helpful hint, because this is going to be more relative to when you guys turn your lab in, make sure and do kind of like, you see how these students, they have the hazards, the list of all the chemicals that they're utilizing. Make sure that you utilize like a hazard table, so that way that you know which chemicals that if we were going into lab, that will be dangerous. So just go ahead and add that into your pre-lab. And Patrick, thank you. That's good. And I think I got everyone. Let me see. Andrea. Great. And if you can just scroll down a little bit. Yeah, so kind of like these, whenever you create the your little hazard tables, this shows all of the stuff that we'll be utilizing. Awesome. Oh, thanks, Andrea. Okay, and I think the last one was Brittany, so you're good to go, Andrea. I got your credit. Okay, great. Yeah, and there's your table. Great. Okay, awesome. Thank you. All right, so it looks like we're good to go. Great, so we have no stragglers this time around. And so awesome, yeah, make sure that, you know, even if I don't call your name, you gotta have it ready as if we were gonna be walking into the lab and you were ready to perform the experiment. And let's see, and yes, this lab is awesome if you're referring to the lab I'm in right now. So let me open up the lab manual. Okay, so this may be confusing to some of you. Maybe it's pretty simple. And so effectively, these two go hand in hand together: TLC, thin layer chromatography, and column chromatography. TLC is the method that we test chemicals in order to check, you know, how polar or non-polar they are, and that is in turn how you can see the RF value of when a molecule moves up, if it's more non-polar, moving with your mobile phase, or if it's more polar and staying with your stationary phase with regards to the silica plate. So this is a brief understanding of the word chromatography and where that came from. The important thing within TLC, the mobile phase, always remember mobile as in that, because the solvent or liquid or gas that they're referring to here is moving. So it is the mobile phase, as to where your stationary phase, silica plate, is just stationary. You know, it just sits there. You place your compound onto it, and the mobile phase is what moves your compound with it, regarding to how non-polar that your molecule is. If it's more non-polar, it will move more with the mobile phase if you're using the non-polar solvent. However, if it's more polar, it's going to be less likely to move, so it'll stick more to your plate. So if you run it and it has very, very, very small RF value, then you'll know it's more polar because it's binding to your polar stationary phase. However, if it's moving up with it, then it's more non-polar because your mobile phase is non-polar in this case. So always make sure to learn the distinction between non-polar and polar. Very simple example, water versus oil, right? So oil, hydrocarbon chains, we can think of that as our non-polar situation. However, water, you know, hydrogen bonding, extremely polar. And then we have a myriad of solvents that, you know, they have different polarities. You know, you can even look at ethanol as a primary example, and that is mostly polar. However, it does have 2 carbon chains on it, making it slightly non-polar. So that is why we use different solvents in the lab, different mixtures. I think I spoke about last time, ethyl acetate and hexane for recrystallization. Those are nice because hexane is just a long carbon chain. However, ethyl acetate is a carbonyl group as well as an adjacent, you know, ethoxide group attached to the acetate. And those 2 oxygens, as you know, will perform hydrogen bonding, leading to it being more polar than hexane, which is extremely nonpolar, only participates and those hydrogen-carbon interactions in between each other. So, look through a good list of different types of solvents, and you'll learn which ones are more non-polar and polar. And there's even tables you can look up called polarity tables on Google, and it'll show you a good list of them. So if we go through and we look forward down here, since we've already discussed the mobile stationary phase, then you'll be calculating here the partition coefficient, where the compounds separate into separate regions called migratory bands. So you can see here in the left, you have a mixture. You would take this directly out of a reaction, and then you just have some, mixed compound in there, right? You take a spot and you place it on there. This is not a very good image because you wouldn't just streak it across. As you guys know, when you read forward, you would just do a dot. When you place that dot, then you run the solvent, and the solvent goes up the TLC plate. And what happens is that the more polar compounds stick to your silica gel TLC plate, as the non-polar compounds start to slowly move up with your mobile phase, which is the non-polar solvent. So always make that distinction of within the TLC system, that the TLC plate is your polar stationary phase, attracting the polar compounds to it, and the mobile phase is the non-polar solvent, making the non-polar compounds move upward on the TLC plate. So, this here is a brief overview as to the, forces that are happening here: electrostatic and dipole-dipole interactions, hydrogen bonding for our more polars, compounds hydrogen bonding onto your silica plate, being unwilling to move up, and then, complexation and van der Waals forces for your non-polar compounds. So moving forward, there is a list here of some stuff that we will be covering within the class, as well as possibly within your other chemistry classes: TLC, HPLC, which is a method of separating out compounds due to their polarity; gas liquid partition chromatography, GLC, as also known as gas chromatography, which we will be utilizing later on within the class, but not today. So TLC, as we were discussing above, here is a way better example, because this is how you'll do it in the lab. You'll take a little pipette, take a drop of your reaction mixture, place it onto the silica where you've scored a line, so that you know where your starting compound is going to be, and then you can measure your RF value from where it's moved. So as you can see, with time, the solvent slowly creeps up the TLC plate, and then it separates your compounds by polarity. So at the bottom here, 2.9 centimeters, you would know this is way more polar than the one here at 8.3 centimeters. And so, yes, you apply it to the absorbent. Then let's see what else. In the developing chamber. So whenever you perform it, you'll perform it into a beaker like this. This is your developing chamber. What it does is it encloses your non-polar solvent or mobile phase, because what happens is that hexanes, they're very volatile, and so they will evaporate. So the main thing is to keep everything in here, because you want to utilize a small amount of solvents that will be below the line that you create with your compound on it. And you'll always make sure that your solvent's below it, because otherwise, if you place it and then it's above it, your compound can actually fall into the solution, and it'll just streak on the plate, and you'll get a very poor example on your TLC plate of the separation of your polar and non-polar compounds. So let's see. So yeah, saturated atmosphere of your eluent or eluting solvent, which is the mobile phase. Again, these words are interchangeable. And let's see. Oh yeah, so filter paper, I believe this would be just to kind of like hold your TLC plate. Not entirely necessary. You can just run the TLC within here, but if you look here closely, and I'll try and see if I can scroll in. Yeah, this is good. So you see here, like the example I was talking about, you have your dots. Let's just say you ran 4 mixtures here. Then your solvent is below the line, always below that line, so it does not take your compound and then just drop it straight into your solvent, and then just messes up the whole TLC plate. Okay. So notice the level of the spots, always above the eluent or mobile phase. So going forward, just some general information. I'm stating exactly the solid adsorbent or the stationary phase is alumina or silica gel. And most of the time you'll run it on silica gel. So let's go forward and let's see. Okay, and now this is coming down to where what I was talking about at the start here with regards to the polarity of molecules. So you can review this here and it will show you the increasing absorption on polar stationary phases. Right here, RCO2H. If these are confusing to you and you're not really sure what this nomenclature is, you can always feel free to search this on Google and it'll look it up for you. But for example, this would be a carboxylic acid. This will be an alcohol, for instance, as an alcohol, ethanol, extremely polar, an amine, and so on and so forth. Going forward, this is less polar as we go to the right and increasingly polar as we go to the left, increasing hydrogen bonding, more intramolecular forces that are keeping it bound to your stationary phase. So that would be, a compound such as a carboxylic acid or benzoic acid that would stick onto the plate stronger than, something over here, like a halide. So going forward, let's see. So yeah, this is just explaining here regarding your eluting solvent or your mobile phase and giving a little bit deeper understanding into it. And so if we look into figure 2.5 here, the eluting power of solvents as a function of polarity of stationary phases. So with our polar stationary phase, which is the silica gel or alumina in this situation, the eluting power with regards to using something like petroleum ether would be very good for something that is very nonpolar, and then all the way opposite would be water for something that's more polar. However, as you increase the polarity of a solvent, you can't run a TLC plate in water just because it will effectively just soak into it like a sponge. So whenever we run TLCs, we wouldn't want to go anything much more polar than ethyl acetate. And this is just more so a scale to show you guys the polarity. It doesn't actually show you the polarity index here with numbers, but if you look online, you'll see the relative polarity for each one here. So yeah, if you ever want to look that up, just make sure to go to Google and search up polarity index, and they'll show you a great example. Maybe I'll pull one up here in a second so you guys know what I'm talking about instead of me just saying these words with no figures. So let's go forward. And we go into the analysis of a TLC. So what happens? You put your stuff on there and then it goes up the plate. Well, some things are colorless. So that's a little difficult because I don't have X-ray vision. You might, but I don't. So we're going to go forward to utilize methods for us to inspect our TLC plate. Okay, and everything will be directly posted on the Zoom or afterwards. I'm going to figure out where to post these videos in case anyone misses out on a part of the lesson, and so that way they can review these videos later. I didn't have last week's pulled, but a lot of you who had emailed me, I corresponded with you guys to assist you with any questions that you may have. So I will make sure to figure out by the end of today how to upload, or maybe I'll just put it on YouTube and then I can just give you guys a link, and it'll be easiest. So that way, because Canvas only holds 2.7 gigabytes and each lesson is about 800 megabytes. So that'd only be like, 3 videos I can post. So moving forward, we will go ahead and see that some compounds, they may fluoresce. So we actually utilize a UV lamp. You've probably seen them in a lab. I can't really recall if it was in Gen Chem lab, but effectively you would use a little UV lamp. It's like the same thing as if you used a flashlight, except you would be utilizing a UV filter or UV luminescent light bulb that would shoot UV ray onto your TLC plate, and it would actually illuminate the spot that is fluorescent under UV light. However, under normal light, which is in the light that we have in here, we wouldn't be able to see it, or a visible light is what they would call it on that side of the spectrum. So as well, moving forward, there are plates that have fluorescent material part of their coating. And let's see, so another one that's really nice is utilizing different sorts of of reagents that you may spray onto your TLC plate, such as sulfuric acid, KMNO4, potassium permanganate, phosphomolybic acid, no clue what that is, and anhydride. I utilize this in the advanced lab to show our students some TLC plate that we had. So, they ran a spot and then they go, where is it? So we take our anhydride, we spray it down, and then you actually take the TLC plate and you place it onto a heating plate. You heat it up, it evaporates in anhydride, and then that actually stains your plate and shows, a good little spot. It's kind of like whenever you have, some water and it just, you leave it on something to dry, and then you come back later and then you see, oh, hey, look, there's the calcium carbonate that's within my tap water that evaporates. It's kind of like that in a way, as sort of a weird metaphor for you guys. Thirdly, iodine is awesome. I personally love using iodine, other than the fact that it is, slightly toxic. But basically, you run your TLC plate, right? You let it evaporate, can't see anything. What do? You go, boom, take a little container with iodine in it, boom, toss it in there, close it up, boom, shake it. Then you're good to go. Pull it out, then you can see it on there. You just have to be super careful because iodine, you do not want to get that into your skin and or lungs. So yeah, the process is reversible and the spots will fade. So, there's a good practice to always use pencil. You never want to use pen whenever you're running with these solvents, because pen can have some chemicals that may start to streak, or it may even evaporate the pen that's on the TLC plate. So we utilize pencil, just make a little score across it, and you can even circle or put a dot or put a little line where you see your spots as they may start to kind of fade away, especially within the case of iodine. So with regards to retention factor, this is what we had from the beginning. So we will look at this and see that the distance traveled by the substance over the distance traveled by the solvent is going to be your RF value. So you will divide the distance, and we can go ahead and scroll up here since they should have had this down there. Kind of a poor formatting, regardless. Right here, original sample spot, right? Solvent front, up here at the top. That's how far your solvent went. Boom, here's your first one, 2.9 centimeters. Divided by 12 centimeters would give you your RF value. Your second compound's RF value would be 8.3 divided by 12. So that will be your two RF values, and the relative RF value as it goes up closer to 1 would be the more nonpolar compound, and the lower RF value, the closer to 0, would be your more polar compound binding to your stationary phase. So I'm just repeating these words over and over to kind of like, get you guys in the rhythm of understanding exactly what's going on with the TLC plate, especially that we're, not performing this in lab. And if you watch the videos, they're great examples, so you can see visually more than just like seeing a still image. I'm pretty sure within the TLC video, they actually show you the motion of it. So yeah, this is basically just going in further into the concept of TLC. So let's go ahead and switch into column chromatography. Does anyone currently have any questions that they need clarified for TLC? Because the column part will be going further into detail with that.
So I have a question.
Mhm.
You said that if it's polar, then it's as far as the movement of it, it's more solid, it would be less. If it's polar, it moves more, or if it's non-polar. I'm sorry, go ahead.
Yeah, so, okay. So do you remember the phrase like dissolves like?
Yeah.
Okay, so that is where we're gonna start the basis of the conversation. So if it's polar, think of this silica plate is polar, right? So if you have a polar compound, then it will want to stick to your silica plate more because like dissolves like, they're both polar. Your solvent that you run, the mobile phase, is non-polar. So if it's more polar, then it will want to stick to the silica plate more. However, if it's more non-polar, you can place it onto the plate and then it'll slowly move up with your solvent or mobile phase that's non-polar. So yeah, we want to make sure, guys, to remember the like dissolves like principle here is super important, because when you utilize a compound, most likely it's on a scale. It's not going to be water. You're not going to place water onto your TLC plate. There's no reason. You're going to be using, these ambiguous compounds that may have, slightly more polarity than the others, or the opposite might be more non-polar. So
Thank you.
yeah, so if you guys have any further questions, feel free to drop them in the chat and I'll try to, clarify it. I try to repeat these things over and over because it is kind of a weird concept, especially, because everyone learns differently and it's easier, at least in my opinion, to learn within the lab. But, I'm gonna do my best to kind of, clarify these things for you. And even if I have to say it a million times, I'd rather say it 1,000,001 and you guys, eventually get it than not say it enough. So yeah, always feel free to email me if you guys need any sort of clarification with regards to our material. Yeah, so the RF value is relative to your polarity of the compound. So when we run the TLC and we calculate our RF value, we see here the 2.9, it would have a lower RF value, meaning it's more polar, more willing to stick to our polar silica plate. However, with the higher one at 8.3, it's more non-polar because it wants to stick to your mobile phase or your non-polar solvent that's running up the plate. So yeah, the RF value is a relative retention value that is relative to the polarity of your compound. The more nonpolar, higher number. Lower number, less polar. Or sorry, lower number, more polar. So moving forward, column chromatography. So this is the solid liquid absorption chromatography, and it is relative to TLC. So what happens is, and this is going to be explaining out in more detail what I'm just going to go ahead and scroll down here to show you guys. So silica gel is the thing that we have on our plate that we run with. And so firstly, we have a fritted disc, kind of like any filter, you would want something to stop the solids from coming through as you run liquid through it. Then secondly, silica, it's actually just like a fine powder, kind of like sand, and you fill your column with it. Then you place your mixture on top of the silica gel. And finally, on top of that, we'll add our mobile phase, which is the solvent, the eluent, onto the top of the silica gel. So the silica gel is still the solid. You have your mixture, which can either be like some sort of like liquid that you place on top of the silica gel, or if you have physical, ground up compound that you place on top of it, it goes on the top of your silica gel. And then you run your mobile phase through and it slowly pulls it through your silica gel. And the relativity of how much your compound sticks to the silica gel is the exact same thing as your TLC plate. Now, the thing here with column is that it runs the opposite way of the way that you see your silica gel. So when you see your silica gel, let me go ahead and just draw a quick diagram for you guys so I can flip it for you because I can't flip it on my screen as fast as I just draw this for you. Okay, so like above, we had the two spots, right? The bottom one's more polar and the top one's more non-polar. And so we know because it sticks more to the bottom spot, or it sticks more to the bottom and doesn't want to rise with our non-polar solvent, that it's more polar because it's sticking to the silica plate, right? So what happens here is that we're not running the solvent up in this case, we're running it down, right? So when you run your column and you start with your compound at the top, and then you start running your solvent down the column, the first thing that's going to come out is the nonpolar. The nonpolar is going to move faster than your polar stuff. So your polar is going to like stick onto the column really well. And the nonpolar compounds are going to come out first. So you'll get you'll start running your solvent, having multiple vials going and going. Let's say you have 100 of them. Well, the first 10 will be extremely nonpolar, your first very nonpolar compound. And then as you go, it goes more and more polar, and you can switch up your solvent. You can make your solvent a little bit more polar in order to start eluting out your compound from it. So as we see here, kind of like the diagram I drew, this is your mixture. So you have your compound at the top of your silica gel. the direction of your solvent flow, right? So the opposite of when we run our TLC plate. So increasing with time, you can see here, all of a sudden now you have your non-polar compound starting to slide down the silica gel. So the reason it's going down is because like dissolves like. It's wanting to follow the mobile phase or the non-polar solvent out of the silica gel. Meanwhile, you have here your very polar compound sticking to the top of the silica gel. And slowly you will elute out the more non-polar first, and then as it keeps going, you'll slowly start to get the more polar compounds coming out of your column. So let's see if there's anything here. So yeah, sometimes you'll be able to see the compound, but again, like with regards to whenever we were saying if you spot it and then you can't see it, that is another situation that you may have like just clear, and you're like, oh, well, I don't have anything there, but you don't know that because you can't see it, right? You don't see it in UV. If you do, you'll be the best chemist in the world. However, most of us cannot. So kudos to you if you can. So we go forward and we will collect all of our samples into different vials and, 1 through 100, then we start running TLCs on these samples to see what do we have. Oh, cool. Okay. In my, vial number 3, I got my first spot and its RF value is super high. Okay, that makes sense, right? Because it's non-polar. When you run it on the TLC plate, it went up the highest. Then, vial number 30. Oh, okay, actually, wait, this spot's RF value is only 0.5. Oh, okay, so it's slightly non-polar, slightly polar. We're about, 50-50. Let's say you run it for 3 hours and then you finally get to vial 100. And then you see, oh, I have like my bottom spot now. Oh, this is extremely polar. It's not wanting to move with my mobile phase, my non-polar solvent that's going through the column. So you would get out your polar last, and in this case, you would get out your most non-polar compound first, because like dissolves like, it wants to move with the non-polar solvent more than it wants to stick onto the polar silica gel. So let me see if there is anything here that I may have missed. Yep, so alumina and silica gel, very common for using as your solid phase, and they have a very uniform size and high specific area. So that way that it makes it, very evenly spread out, and when it's dilute, it's very uniform instead of being all wonky and everywhere. So with normal phase column chromatography, a polar stationary phase such as alumina or silica gel is utilized with organic non-polar solvents as our mobile phase or eluent. Under these conditions, the allotropic series described for the TLC in section 6.2 applies. Where is our section 6.2? Okay, I don't know where that is. So anyways, we'll go forward. There is a topic that some biochemists love, reverse phase column chromatography. And if you have not utilized this, then you may utilize this at some point. And so basically, we have a stationary phase that is glass beads that are coated with non-polar hydrocarbon film. So it would be the opposite of what's happening with the first one with silica gel. This is reverse phase, meaning that when you place your compound into there, the non-polar compound is going to want to stick more to this. So reverse phase means that your non-polar compounds will stick more, whereas when you're running your mobile phase this time, it's going to be a polar mobile phase, pulling through your polar compounds first, and then lastly your non-polar compounds. So just remember, normal phase, polar stationary phase, non-polar mobile phase. The non-polar molecule or compounds come out first, your polar compounds come out last. Reversed phase, switch the page around, right? Stationary is now polar. Mobile is now, or sorry, stationary is now non-polar. Mobile is now polar. So everything that you know about the silica gel situation, silica gel stationary, polar, mobile phase, non-polar, switch that around. Non-polar is your stationary phase and polar is your mobile phase. So as we can see here, Mixtures of water and organic solvents are generally used as the eluting solvents. However, we would use more of the stuff up from here. Instead of utilizing stuff like petroleum ether, hexane, toluene, we would want to be using water, methanol, ethanol, propanol, and then kind of like the opposite situation would happen here where I said like you don't really want to use anything above ethyl acetate in terms of polarity. The opposite switches here for reverse. So you'll probably not want to use anything more nonpolar than ethyl acetate in this situation. So everything that you see for normal phase, just switch it around in your mind when you hear reverse phase. So let's see, let's go back here. The order of elution is reversed than shown earlier, with the more polar compounds eluting more rapidly than the less polar, because the less polar compounds will stick to your glass beads coated with nonpolar film, whereas your polar compounds will want to come out with your mobile phase. So again, here it's the exact opposite of the list that we had above. Now the absorption rate is much higher for the compounds on the right, whereas something like the carboxylic acid, it wants to elute faster with your more polar solvents. So going forward, anything that's critical, these are just some little minor comments that you'll still want to read through. I just want to make sure that I hit on the most important things here. So let's see. So right here, they're kind of saying here that you want to use as little as 10 grams of adsorbent for each 1 gram of mixture. However, whenever it has similar polarities, the ratio must be increased to as much as 100 to 200 grams to 1 gram. So normally we'll use a good measure in the lab is around 25 grams of your stationary phase to 1 gram of your compound. So 25 grams silica gel for every 1 gram of compound that you utilize. And so the ratio of the height to diameter, and that's relative to, the column is a long tube or a long glass cylinder. They would want it to be about 8 relative to 1 of your mixture compound. Okay, so your column is made of glass fitted with stopcock. So that was kind of like relative to the image that we looked above. And we're going to look at another image here in a second once we get through the rest of this. The method that we prepare our column with is, one would be the dry pack method. So you pour your silica gel slowly into a vertical glass column, half filled with solvent that will serve as the elutant. The other way around is to wet pack it. So you take a slurry of your adsorbent, which is the silica gel, and your eluting solvent, let's just say, petroleum ether, hexane, and then you add it into the column. They say that this is the preferred procedure when silica gel is absorbent. So whenever you prepare your column and you place it in there, then you kind of have to tap the column so that way that you get everything uniform and so that you don't have any air bubbles that'll separate your compound and maybe make it, slip through. And then all of a sudden you get all this weird packing and it will not separate as well as it would if it was uniform. So talking about air bubbles. And like I said, uniform packing of the adsorbent is essential. The solvent will move down the column with a horizontal front. So an additional assistance here to place layer of sand, because sand is neutral. So we will utilize the sand to allow the sample to float evenly, as well as if it prevents disruption of the packing material, because what happens is if you have your mixture on the top, right, you put your solvent in, and what happens if it just like splashes and your compound kind of like goes up on the walls of your glass. So this sand acts as a secondary filter, kind of just to make sure that your compound doesn't splash around up on the walls and it stays uniform and packed within your column. So yeah, you use a little bit of solvent to transfer your solids into the top of the column. Otherwise, yeah, like I said before, liquid mixture, you can just put it right on the top of the column. And let's see. And yeah, so you only want to use a little bit, just because if you use too much, that band, instead of it being like a really tiny, small, uniform, very nicely packed band, it can become like really big. And then all of a sudden, you have a big band moving through your silica gel, and then it's kind of some of it will attach more and you'll get separated. And then the idea is to keep it uniform so that way that you get it, uniformly moving through your silica gel and not like, oh, here's this massive amount and then, okay, this part's going and now this is kind of crossing and you have a very, very mixed separation. So you'll want to reduce the amount of excessive solvent that you utilize within your compound mixture that you place on top, just so that way that you get a very nice uniform separation within it. So this just describes the statements that I was making with regards to adding more solvent, letting it run through, et cetera, et cetera. So yep, using TLC here because it's a lot of the compounds in organic chemistry are not visible. So within if we were running this in lab, we would use TLC on this, and so we would be separating fluorine and 9-fluorinone here. Okay. Yeah. So let's see. So this would be utilizing TLC to identify the difference in polarity between fluorine and 9-fluorinone. Okay, yeah. So you use the solid mixture determined by TLC to separate a mixture of fluorine and 9-fluorinone by column chromatography. And so we would run, our TLC on these two compounds here, and then what would happen is, we would see one spot would be higher than the other spot, meaning that the higher spot is more nonpolar, and the other spot is more polar. So in this system here, we'll be using PET ether and dichloromethane as our mobile phase, and be using the TLC plate as silica gel as our stationary phase. So yep, silica gel. Yeah, so you only want to handle the sides because if you touch it and you get oil on it, it can kind of mess up the plate. It would mess up the separation of your bands and maybe like, shift the dots over a little bit and just, we always want to utilize it with gloves and to hold it on the sides of the plate so that way we just don't get anything onto the plate. We're not trying to analyze. The pencil dot, this kind of just goes through all of the steps here. And I'll just show you guys the instructions in this other slide here so that way I don't just bore you guys to death by reading you out all of the instructions here. So after we run all TLC, we would identify which one is more nonpolar and which one is more polar. So then this would be the setting up system, utilizing here our stationary phase and setting up our column for chromatography. Then putting our PET ether in there and adding dry silica gel, and this just, packing up our column, getting it ready. Then we get our sample with a mixture, suspend it into some petroleum ether, and then add DCM, dichloromethane with a pipette. Going forward, we'll just kind of skip through because this is more and more of the systems that I was speaking about above. Slowly you collect 5 milliliter fractions, and then you would see. This would be, how many milliliters that we've added into our column going forward. So I guess we would see that the first one we get would be fluorine, meaning that it is more nonpolar because we're using our nonpolar mobile phase, whereas the fluorinone is more polar because it is coming out last with our mobile phase being nonpolar. So make sure that you read through the lab manual once again in order to understand the answers with regards to your post-lab questions. And we will look here to see another drawing kindly drawn by our professor where we would add in our petroleum ether. Let me go ahead and see what we have here. Explain the graph again. Yes. Let me go ahead and get through this really quick and then I'll go back up. So you add your petroleum ether into here, you have liquid into here, your stop clock's closed so that way no liquid comes out. Then you add your dry silica into your liquid here. Then afterwards, then you can go ahead and add a little bit of sand and in that way that it'll pack your silica. Then you add in your mixture of your compound in order to make it bind very kindly to the top of your silica here. And remember, the sand is neutral. So the sand is just there to make sure that it doesn't splash all over the place when you add in your mixture compound. So coming back to the chart that was requested to be reviewed, here, this is 5 milliliters, then 10, 15, 20, 25. So this is the increasing amount of milliliters of sample that have been run through your column. So 5 milliliters are collected, and then the next 5, and then the next 5, and then the next 5. So we go through individual vials in order to separate our compound, and each vial, the very first one will be the most nonpolar within this system. The very last one would be less polar. I'm not going to, or sorry. The last one would be more polar. I'm not going to say that it is polar because it still isn't technically. You're using a non-polar mobile phase, but it is less non-polar because the most non-polar comes out first. If it's a non-polar mobile phase, then the more non-polar will stick to your non-polar mobile phase and come out firstly, such as the fluorine here. And then your more polar comes out last because it's binding to the silica gel more than it is binding into the mobile phase. Yeah, we'll have to review the data that I give to you guys. So yeah, but it'll be something relative to this, and it would be a relative amount. Let me see, what are they saying with regards to the scale? Yeah, so a scale of none, some, a good amount, a bunch. Terrible scale. However, we'll go forward with it, and we'll see that if you saw this in the lab, you would notice by a TLC plate, when you first go and you use this none, you wouldn't see a spot at all when you run your TLC.
You'd see a little spot. My speaker just died, so hopefully you guys can still hear me. So whenever you would run some, then it would show like a stronger dot, and then when you'd see a lot or a bunch, then you would see a very bold spot running on that. And then as you keep going, you would see the spot slowly become like smaller again, and then eventually you'd have no spot at all. If you ran individual like TLC 1, 2, 3, 4, 5, 6, like if you ran each individual one, and that is a common practice within lab, that you will run, samples 1 through 10, vials 1 through 10. Oh, okay, cool. Oh, it's getting stronger. Vial 4, that's the strongest. And then, oh, okay, now it's fading away. Okay, now we're getting a new band over here at vial 20. Oh, and then you would run it, and then you would see vial, let's say 4 was super good, and vial 22 was really good. You run them, and then you'd see the first one would be really high on the TLC plate, super nonpolar. And then vial 22, it'd be like in the middle of the TLC plate, more polar, less nonpolar. So that's the main thing, is to get the distinction between the two. So let me go over to his nice little presentation here. And it had part of, so let's see. So firstly, here's our beakers. Then we have our different solvent systems here. One is dichloromethane, slightly polar. One is petroleum ether, very nonpolar. And then here's a 3 to 4 or 75 to 25% mixture of petroleum ether to dichloromethane, meaning that it's mixing the polarity because you're mixing two solvents with each other. Effectively, since you're adding petroleum ether into DCM, you're going to be making it more nonpolar than just pure DCM. Pure DCM would be way more polar. So cover each beaker with a watch glass, and then you prepare your TLC plate. Each TLC plate, you would want it at about the same height. 2 centimeters here is what he's saying, or 1.5. Then place your TLC plate into the chamber. Make sure that your mobile phase is under the line. Put the watch glass on top to keep the solvent from evaporating out. Then after 10-15 minutes, develop it. Then you will see the difference. So you see here, the first one ran in only DCM, your two spots are like really high up here. They're pretty close. Not very good. The reason it's not very good is because the polarity is too close together within this solvent system. So it's better to run something like in petroleum ether. Here you can see the spots are much more separate. This is showing that this first spot, the fluorine, the fluorine is very nonpolar, and then the 9-fluoronone is very polar, sticking to the plates and way more polar. And then if you use a mixture of 75% petroleum ether to 25% DCM, you see it kind of still has the spots together a little too closely. This one's really nice. I would personally, if I was running in the lab, I'd run petroleum ether for this specific compound, just because you can see there's such massive separation of the two. And again, this is the same drawing that we reviewed from before with regards to add your petroleum ether, make sure that the stop clock's closed. Then you add your silica, open it up so that way that you can start running your solvent through and packing your silica, and it slowly becomes uniform and ready as a stationary phase to add in your compound. You add in your clean sand to establish uniform, make sure that it's level. Then you add in your mixture of your compound. Then you would start running your sample, and it would slowly start to move through your silica gel with your mobile phase of utilizing the mobile phase of petroleum ether and DCM, dichloromethane. And you would slowly start gathering vials, vial 1, 2, 3, 4, 5, 6. And each test tube, what they're doing here is taking a little spot and then they put it onto a watch glass. As you see, the spot's getting bigger, meaning there's more of your compound coming out, and then slowly it fades away. So more of your fluorine comes in, and then it starts to go out. Then the following test tubes, like 7, 8, 9, 10, that could have been labeled better here, but anyways, they would start to come out yellow, meaning you have your 9-fluoronone coming out. As to 1, 2, 3, very big, very large amount, kind of relative to the graph we saw that at the bunch, and then slowly that would fade out. So yeah, this is the separation of your fluorine and 9-fluoronone, showing that the fluorine would be more nonpolar than the 9-fluoronone, and for the reverse statement, 9-fluoronone is more polar, whereas the fluorine is less polar. So the main thing here, the take-home lesson, is to understand the differences in polarity. And let me go ahead and open up a picture for you guys so you guys can see a polarity index. If you guys have any questions currently, feel free to go ahead and type them out. Otherwise, I'm going to pull up the polarity index for you guys, and then we can go ahead and close off the session. And let me make sure if I didn't have any stragglers, so I don't miss roll, because I don't have a very efficient roll system. Right, so if I look up 9-fluoronone polarity, let me see. So if we just look at the molecule itself, I just closed everything out that I had. Let me reopen this real quick. So yeah, this will be a good way for you guys to look at this right here real quick. So if we look back here, fluorine is more nonpolar and 9-fluoronone is more polar. The reason 9-fluoronone is more polar, the biggest example here that you guys should see is this ketone. So that's an oxygen. Oxygen performs hydrogen bonding, making it more polar. However, it does have aromatic groups on here as well as more carbon chains. So it's not explicitly a extremely polar compound. It just has more polar characteristics than the fluorine, which is just a ton of carbon chains, 2 aromatic groups, no oxygens, no hydrogen bonding. However, 9-fluorinone, like I said, has the oxygen here, so it would exhibit hydrogen bonding, whereas the fluorine would not. So yes, 9-fluorinone is more polar, fluorine is more non-polar. So finally, let me go ahead and open up this polarity index for you guys, and then we can wrap it up. Just go ahead and share my screen. Be easier. Okay, so if you look onto Google, you can find these polarity indexes showing pentane as extremely nonpolar, heptane, hexane, petroleum ether 0.1, and then if you look all the way at the bottom, 1,4-dioxane, not very relevant. Ethyl acetate 4.4, much more polar. Let me see if I can get one with water. Yeah, water 10.2. So the higher the polarity index, the more polar that a solvent system is, such as ethanol, even 5.2. That's even more polar than it is nonpolar, right? Because something like pentane, hexane, petroleum ether, all down near 0, very nonpolar. Benzene, which is an aromatic group that's on your fluorine compound, very nonpolar. DCM, slightly nonpolar. Now we're going more towards polar. Ethyl acetate, more polar. Acetone, polar. Methanol and ethanol, polar. Going forward, acetonitrile, very polar. And, it keeps scaling. So if you ever want to look, you can just Google over here, polarity indexes, figure out yours. This is a really interesting one. I love this chart personally. If you're a chemist, it's very useful. You can actually look at it and figure out which 2 solvents are miscible together. So this is really nice for if you're in lab and you're trying to make a mixture to create a polarity. So you have your polarity index, right? And you have something like benzene 2.7 and you have pentane at 0. Well, what if you don't want to have only 2.7 or 0? What if you want to have somewhere in the middle, like 1.7? Well, is pentane and benzene miscible? You would go here, you see benzene here, and then you can see, let's see, where is that? Benzene and pentane. So right here where my mouse is, benzene and pentane, those 2 are miscible. So you can mix something with a 0 polarity index with benzene 2.7 polarity index, and those 2 would come together. And when you have those 2 mixed, you would do a calculation to figure out your polarity after you've mixed the 2, and it's relative to the ratio. Very simple math that you can perform. And this chart's really awesome because you can see what 2 solvents you can put together, and they'll actually mix, and they won't be like oil and water. Whereas something right here, water and benzene, you'll have the oil and water effect. You'll have one layer of your aqueous, and then you'll have one layer of your organic, which is also relative to later when we start doing our 2-phase separations. So I don't want to waste any more of you guys' time. If you have any further questions, feel free to stick around and either ask now or type in the chat. Otherwise, you guys are free to go. Thank you.
Hey, Scott. I guess I'm just a little unsure about, so I'm looking at the actual lab manual, and under the TLC, it says, under the analysis part, it says, note the number of spots arising from each of the original spots. Isn't it always going to be 2 because we're all, we're judging for fluorinone and 9, or fluorinone and 9-fluorinone, whatever the 2 compounds are.
Yeah, let me pull this up real quick.
So it's on page, looks like top of page 12.
Okay, top of page 12, and you were saying it says which part?
Analysis. And so it's saying, note the number of spots arising from each of the original spots.
Uh-huh.
And that,
Yeah. So on TLC, that would show you relative to this here. Let me share my screen one more time. So it'd be relative to this section right here. When they say the number of spots, they mean like this. So like you have a starting original sample spot, and then after you've ran your TLC, your solvent goes up. Then you would have the more polar here at 2.9, your more non-polar here at 8.3. So they're just saying to note how many different spots that you have on your TLC plate after you've ran your solvent.
I mean, but like, my question is, isn't it always going to be 2? Because we have
That's relative to how many compounds you have in your mixture.
Right, but in this particular example, we're always using the 2, aren't we?
Yeah, I think that they're just making sure that you quantify the numeric amount, so that way that you understand the concept that they're placing in front of you. So yeah, if you had a compound or a mixture that had 4 compounds in it with different polarities, then you'd have 4 spots. So yeah, in this example, it's 2.
Okay. I'm just not super sure how to fill this one out.
Question.
Mhm.
This is regarding like the quizzes. So I had noticed that from the last quiz that it has some of it is for the week of, and then some of it's going to be for next week. Is that always how it's going to be?
Let me go ahead and write that down as a note, and then get that back to you.
I actually had a quick question. So for the homework, are we supposed to be like, it's a little different from last week, but this week, are we submitting the pre-lab and the like post-lab questions together? Because I noticed in Canvas it said something about that.
Let me see. Where on Canvas did you see it? Because primarily we would want to only submit your entire notebook together.
Okay, well, I guess I phrased it wrong. The notebook, what does it completely encompass is my question.
Yeah, the pre-lab and the center of the lab notebook, and then the post-lab. Always refer back to the syllabus for the full formatting. But when you submit the lab notebook, it'll be everything: the pre-lab, lab, and post-lab.
Okay, so then you would recommend just strictly doing it online instead of like taking the picture, converting it to the PDF?
Yeah, it may be easier. If it seems easier for you, then yeah.
Okay, and then my last question was, you made reference to something saying, I was taking a note. It said the higher the polarity index, the more polar or more non-polar it'll be.
Yeah, the higher the number in the polarity index, the more polar. The lower the number, the closer to 0, the more non-polar.
Gotcha. Thank you.
Yeah, and that's a little extra that I just kind of tossed in there because it's relative to like being in lab. I don't think that the polarity index was really mentioned much within this lab manual, so that's kind of just something I wanted to show you guys to give you a little bit more of a scale instead of just saying water's polar, petroleum ether is non-polar. It's like, how much though? Numerically, what does that mean? So.
Thank you.
Are you going to like put notes as to what we should improve for our next lab? So like if we get points off, we know like what to fix?
Yeah, and I can definitely make some little comments. So I'll go ahead and get these reviewed before this lab notebook is turned in. And then if I see any generic things, kind of like the first quiz that we had, then I can make general comments. So that way everyone knows, just to make sure to hit those specific little things so y'all don't lose any small points.
Okay. And is there a list of like what all chemicals you should do the hazards for, or just like anything besides like water and acetone or something like that?
So yeah, you're gonna just want to list out every single chemical that would be utilized within the lab manual for each individual experiment.
Okay. Okay.
Yeah, anything that you see listed, just go ahead and toss it on there. So just in case.
Alrighty. Well, thank you. Have a good weekend.
You too. Thanks.
I have a question about the hazards,
Mhm.
how can you tell, or how do you know if it's an organic waste or an aqueous waste?
So hold on, let me just write this note down real quick. So organic waste is anything. So basically anything aqueous waste is water, or anything soluble into water, and anything that is a compound or organic, such as any of the solvents, petroleum ether, dichloromethane, ethyl acetate. Those are all organic waste. So basically, the only thing that you will need to know that is aqueous waste would be water, or some things that we would dissolve in water, like salt, you know, or calcium carbonate. Some of these more inorganic compounds, but those would be considered also solid waste. So the main thing to know is that water is aqueous, and then any of the solvents that we utilize in lab are organic waste.
Okay, thank you.
Mhm.
Have a good one.
You too. Alrighty, does anyone else have any further questions before I go ahead and end our meeting?
I
Just
have a
a
question about the quiz.
Okay, go ahead.
Mhm.
No, I was just asking, my previous question was that if the quiz would encompass both this lab and next week's lab, and if that'll always be the case.
Yeah, so I'll go ahead and talk to Dr. Stogie about that this afternoon, and I'll
Okay,
email you,
sorry.
or I'll give everyone a general notice.
All right, thank you.
And just quick question, the only calculations that we're going to be calculating is the RF. Is that the only one, correct?
Yeah, and then if they ask you to do that kind of like chart, I'm not sure if that was a part of the questions there. Let me see. But yeah, RF value would be your calculations, and even with the other one, that's not a calculation, right? Because that's just a graph. Let me see in TLC. Yeah, so it looks like it's only going to be the RF values relative to the compound, or the data that you look at on the canvas.
Oh, thank you.
Mhm.
Have a good rest of your day.
Thank you. You too.
So Scott, I'm looking at the data we're provided. I'm not 100% on how to do this. Like so the first at the TLC, I understand because we have the plates, and so we can do the RF values from that and all that. The second part, I feel like I'm missing something. So this gives us, this is sort of a scale thing talking about 0, 1, 2, 3,
Hey,
start with.
doing good.
I feel like I don't see the actual data for this. I just see the scale. And so I'm like, I don't know how to.
The data that you would analyze would be relative to your first name. So you would look at the data for section 2, since your first name starts with J, and that would be where you would do your RF calculations off of.
But aren't we doing the column thing where we're also like noting the where you do the smear for the PE, and then you do the check, basically the relative yellowness for the.
Yeah, so then you would look at, you would utilize the data on the second page as well to see within the first section, since your name starts with a J, and you would quantify the amounts given on that watch glass there on page 2.
I don't understand how to quantify that, or even where I'm starting from.
Well, you would look at the image, and then you would quantify the relative amount relative to none, to some, a good amount, and bunch.
I guess I'm just being a dummy, but I don't understand, like, how do I quantify which one is number 1 when it's just a ring?
Well, that would be you'd have to take an educated guess there. I can't give you the answers directly to it, because it's pretty intuitive. Just look at it and give it a scale. That's the only thing I can say toward it.
Okay, and there's 10 of these. Okay.
Just give it a relative scale. I'm fairly confident that you you'll know the difference between a bunch and none.
Mhm.
Don't take it too deeply, you know. Just give it a good relative scale.
I think I understand, but
Yeah.
like that's one. That's the first one. That's the essentially the PE smears, right? But what about the DCM where we compare yellowness? Are we just not doing that part? Because how are we doing the fluorine?
If this is the only data given to you, I would say that you would only you know, answer relative to this section for your data to complete in your notebook, and then just answer the data analysis section.
Okay.
It's going to be very minor. It's not going to be the same way that it would be if we were in lab.
Okay, that's what I was trying. I was just trying to transpose exactly how we do it in lab onto here.
Yeah, no, it's not going to be relative, unfortunately. Just answer the data questions that are there, and then answer the post-lab questions here that are on the lab manual.
Okay, and one last sort of formatting question regarding that. For the post-lab questions, should we be putting them under data and analysis, or should we put them like at the bottom under conclusions as a separate thing? Do you care?
I would say put them into data analysis. Yeah, put it before the conclusions. Conclusions will just wrap up the ideas given to you for the lab.
Right. Okay.
Yeah, that's more of a generic, like kind of written, like if you were writing a research paper-esque situation.
Okay, fair enough.
Yeah.
All right.
Okay, yeah, and if you have any other questions, always feel free to email me, and I can help you out with the, you know, kind of giving you little hints.
Okie dokie. Thanks so much.
Okay, have a nice day.